Yeah. Brian has already introduced me. Thank you, Brian. But to say about myself, talk about myself, I'm Phillip Porras from Accuknox. My primary expertise has been into transport optimization. I've worked on several transport layers, including quick, multi-part transports. I worked in the security domain, especially in the PKI solutions for general enterprises. And my specific yeah, There's one area which I specifically like is about IoT networks. In ITF working groups, I've been a regular contributor, and I have RFCs to my name, and there are several working group documents in ITF that I'm working for. Uh, okay, I'll send the slide deck to everyone after my talk. Uh, I'm going to talk about KubeArmor. KubeArmor is Kate's native solution for system policy, audit, and alert and enforcement engine. Now, wo- system policy, audit, and alerts is something which is not new, but the enforcement part is something which is unique to KubeArmor, and I'll go ahead and explain what it is and how it makes sense. But before that, going into the details, let me first explain the problem statement. Now, one of the things that we came across is whenever people talk about container runtime security, most of the time they equate it to network security. And network security is kind of important uh, because that's what gets the attacker within you, inside your network. But apart from the network security, one has to concentrate also on the system security and the data security. At Accuknox, we are trying to deal this problem in a holistic way. We have a complete runtime security solution in the form of network plus system plus data. And I'll go ahead and explain what KubeArmor does in the context. Now, the other problem statement that I'm going to talk about is there are Linux kernel primitives available for handling system security, and it's been widely used today. SLNX, AppArmor, those are widely used. All the cell phones, all the smartphones are already equipped with SLNX based protection. Having said that, why these protections points are not covered by the Kubernetes platform, or what are the limitations with respect to Kubernetes platforms, and how we're trying to get around those problems, and what is our future roadmap towards making sure that this open source scales to enterprise and system security in general. And the next aspect is about the runtime securities for systems and applications. Basically, the compliance and hardening standards. I'm going to talk about some basic compliance and explain why system security makes so much sense in the context. Uh, to begin, the existing solutions we have, I'm sure folks might have heard of Falco and Tracy. Both of them have an integrated have integrated eBPF backend, and it couples with Kubernetes metadata very nicely, in the sense that whenever there is an audit or alert event, it would give the context, the Kubernetes context, in the context of that particular alert, and you can have rich alerting and telemetry system based on this. Uh, the rule engine is highly flexible. You can put in any kind of conditions. For example, if you want a particular process, if a particular process is found, the working directory for that particular process plus several other attributes, you can take into consideration and then generate an alert. Falco also provides some out of the box rules which can help you with the miter defense techniques. But both Falco is a Sysdig open source, and Tracy is Aqua Security's open source. Both of these are not an enforcement engine. What it means is, even if you can get an audit or alert event, but you cannot block that event from happening. Uh, that's where KubeArmor comes into picture. Now, I'm going to take a moment to talk about system policy controls. This is the MITRE ATT&CK framework for, and here I want to just highlight that there are a lot of aspects which are basically systems related, and not so much. Of course, there are network related aspects, and some of the aspects could be covered by network as well as data security as well as system security. But there are a lot of aspects. For example, Kubernetes cron job, a host path mount, or kube config file, or writable host path mount, bash command inside container. All of these points are to be handled, should be handled by a system's security policy engine. Uh, it cannot be handled as part of network security, so to speak. Uh, Now, when it comes to systems primitives, Linux has got a good breadth about implementing this system securities. LSM's been the primary one. Now there is AppArmor, SLNX, Mac, and Tomoe, and so on. There are so many LSMs deployed, widely used today. There is something called as kernel runtime security instrumentation. This is a work that is in progress in KRSI. This feature this is called KRSI, and this is enabled since kernel version 5.8 and above. Well, the primary advantage with LSMs is that they don't suffer from time to check versus time to use problem. What it means is that the controls are effectively applied in line to the system calls, or LSM hooks, to be very precise. I'll give an example in the next slide. But having said that, these are Linux native primitives. These are not integrated with Kubernetes or Docker. Anyone who has worked with SLNX knows how difficult the policy language is. Getting around, so most of the times I've seen or any SLNX getting disabled just because it is so kind of hard to get it right in the first place. And then there is there is this additional complexity of different versions of LSMs behaving differently, and different kernel versions having LSM spec in a different way. Then there is something called a seccomp, which allows one to sandbox the process. Essentially, you can say that only the specific set of system calls are allowed to be executed within your process or within your container. Docker support is available for seccomp, but it's a one-way transition to restricted state. So once you have moved into the restricted state, you can't go back. Which is a problem if you want dynamic policy enforcement. You might want to add, delete, enable, disable controls at runtime. Dynamic enforcement is not possible, which means that only when the process is started, you need to specify all the constructs, all the sandbox constructs. After the process is started, you cannot change those constructs. This has seen limited adoption till date. I know of one discussion of PGSQL where they were trying to make use of a seccomp, but it didn't fly off because of this highly restricted way of handling things. And of course, there are user space controls, LD preload being the primary one. I'm sure I'm sure you folks here might know of other user space controls as well, but LD preload is something which strikes me instantly. You can override any of the dynamic libraries and hook up the library calls and add your own handling. Having said that, there are multiple ways of bypassing this kind of controls. For example, uh, there are library calls which there are library calls available to make the system calls, but it is possible for the malicious attacker to directly invoke the system call without going through the library calls. So these kind of scenarios cannot be protected with such kind of user space controls. Uh, the next aspect I'm going to talk about is about the asynchronous control and inline control. What I mean by this is, now if you get an audit or alert event, and if you want to block that thing from happening, uh, one way that Falco or Tracy handles it today is that it sends an alert to the user space, and that user space, in the user space, there's a policy engine which will take some action. Usually it could be a kill process, killing the malicious process here. But this is an asynchronous control. The damage might have been already done by this malicious process till the time this process has been killed. For example, if it's a security file or security sensitive file, which is to be deleted, or it's been tried to unlink, the unlink process would have been already succeeded by the time this malicious process is killed. That's why inline controls are sort of important. And that's what LSM is the only technology out there for Linux which allows you to have inline control. So that's what the KubeArmor does. KubeArmor does two things. One is it's basically a Kubernetes native solution. It provides a Kubernetes operator for LSMs. You can think of it from that perspective. It's a Kubernetes operator for LSMs. You specify the policy in regular YAML format. It goes ahead. It orchestrates those policies through Kubernetes and makes sure that all the nodes, all the containers for which the selected labels have been specified and the namespace has been specified gets applied those controls. Those controls are internally applied using AppArmor and SLNX, but before applying the control, it takes into account which AppArmor, what is the Linux kernel available, and make sure that the appropriate policy is created in the appropriate context. Now, there's an eBPF part to it. What happens is the LSM technologies in general do not care about Kubernetes. So whenever there is an audit and alert event, the eBPF monitor here intercepts the audit event and makes sure that it adds its own metadata. It makes sure that it adds the metadata about the container, the namespace in the context, and then flushes the audit event into the corresponding file or to the /1 log audit or logs, something like that. So basically, this allows us to make sure we can have actions which could be audit actions, or we could have block actions, and we have the rich alerting engine which takes into account the Kubernetes metadata, and all this is done, all the backend is handled through LSMs. In the future, we see kernel runtime security instrumentation being a vital element to the overall KubeArmor strategy, because essentially what KRSI will allow us to do is it will allow us to specify the policy details as an eBPF bytecode. eBPF is a lightweight runtime, virtual machine sitting right inside the kernel, which allows the user space to specify a constrained bytecode to the Linux kernel. Using the Linux kernel, you have to specify two things. One is the bytecode, and the other is the hook point. So whenever that hook point is hit, that bytecode will be executed. Now, network security has been radically changed because of eBPF, Cilium being the primary open source which is taking into consideration, which is making sure that eBPF is used appropriately for network security. But the same is going to happen for system security policy enforcement also, and we see KRSI as an enabling point towards it. KRSI will allow us to use eBPF bytecodes at LSM hooks, which means that we won't be limited by the constructs that are provided by AppArmor or SLNX. We won't be constrained by the policy, the language constructs that are provided by SLNX or AppArmor. It will be much more flexible. The way I see it, the thing that happened to IP tables and NetFilter when eBPF came in, the same thing is going to happen for LSMs when AppArmor and SLNX when KRSI is going to join the party. I've already talked about this. The design elements, it's a Kubernetes operator for system-wide security policies. You can specify, you can have the Kubernetes native YAML policy specification, which in turn gets converted into AppArmor specification or SLNX specification, depending upon what you have in the context. And again, in the context of multi-cloud, you have GKE, which supports, which has container optimized OS, and it ships by default with AppArmor. On the other hand, you have EKS, which has Amazon Linux 2, which ships by default with SLNX. From the administrator perspective, now the administrator doesn't have to understand both AppArmor and SLNX at the same time. KubeArmor will make sure, to convert the policy specification, the YAML policy specification into appropriate AppArmor or SLNX specification in the backend. So essentially, KubeArmor makes sure that, the LSM's deployment complexity is handled at its end. And of course, this point is also important, but this point is also being used in the same. The way Falco and Tracy handles it, the KubeArmor currently handles it in the same way. There is no new thing here, but it's sort of vital to the overall operations. There is a demo video. I'm not going to exactly show the demo here, but we have a demo scenario where you have a WordPress and MySQL application, and these are the 4 points that can be handled through KubeArmor. You can edit all accesses to a particular path, warlib MySQL. You can block any credential access by unknown process. WordPress stores all its configuration information in a particular file in its container, and outside of the WordPress application, no one else would be able to access those particular credentials, or won't be even able to open this particular file. Blocking the execution of specific processes within these 2 containers, you can specify a set of processes which could be restricted, which would be given and restricted access. So this is a block operation. And also making sure that the service account token that is mounted should not be allowed to be accessed by anyone else outside of the Kubernetes API server. So these are some of the example policies, and you can see here that the action could be audit, which is very similar to what uh, Falco or Tracy does. But you can also have an action called as block, which is essentially the enforcement point. The same 4 points that I've mentioned in the previous slides, these are the sample YAML policies to it. And here below it shows how it maps to the MITRE ATT&CK framework. Well, I don't, we will be putting up the demo video on the YouTube very soon. We already got it up yesterday. I'll be more than happy to share the link with this team here. One of the important thing for the future work that we are looking at, like I mentioned before, is to integrate with the KRSI engine. It really is going to be powerful once the KRSI becomes a commonplace engine out there. Once the KRSI availability becomes not a problem in the future. MITREs and Sysdig-based policy templates. Now, KubeArmor is in a unique position to make sure that the MITRE and Sysdig-based policies are enforced, not only audited and but also enforced at that appropriate juncture. Building automated policy generation tools is also going to be one of the key thing that we are considering. So it's not a very easy ask to build an automated policy generation tool for systems policy, because of the wide there are almost 300 system calls, uh, and the system calls interception itself is very intrusive. It will impact the performance of the containers and of the host. So it's not an easy ask to get this worked upon. We are essentially seeking community feedback at this moment. It's a very new open source that we just started working on, and we have released version 1.0. Thank you. That's it from my side. Any questions or any? I'll be posting the.
Yeah, I have a question.
Yeah.
So I think it was on slide 3. You brought up Falco and Tracy as kind of the other existing solutions.
Yep.
How do you feel as though implementation as open policy agent like Gatekeeper stack up against what you have?
Well, open policy agent we could integrate with open policy agent as well. So ours is an enforcement engine. We are not an admission controller, so to speak. Open policy agent or Qbarmor, these are different admission controllers. We could essentially integrate with those admission controllers, but it's a different paradigm. It's an abstraction that we are not. Someone can take Qbarmor and work with open policy agent to make sure that all the policies are admission controlled through Gatekeeper or any other open policy agent process or deal.
Okay, so it's more of like a deeper
Yes.
level.
It's an actual enforcement engine which takes into considerations the system calls or the file objects, the process objects, and make sure that the access is limited to that.
Yeah, and keep in mind that open policy agent is not doing any enforcement. So that's basically presenting a policy and making a decision. Should I do this or not? It's up to something else to do the enforcement. And it runs in user space. So this is actually in kernel space. So all the activities happening in kernel space, correct, Rahul?
Exactly. Yes.
Yeah, I
Right.
mean, like the gatekeeper product, from what I understand, and I haven't gotten too deep into it, it actually can, prevent things. So it's not entirely true to say that it can,
Yes.
as long as that's true. But I just wanted to sort of see, like, I think I'm starting to see how like it operates at a lower level.
Yeah. So let me give one example of what gatekeeper can possibly do. So for example, one typical example which is quoted in the context of gatekeeper is that if your container doesn't have a particular label, gatekeeper will make sure that the admission controller doesn't allow that pod to be spawned. Now that's a very Kubernetes specific construct that gatekeeper deals with. So those are the enforcement that gatekeeper handles. It's not at the system level construct that gatekeeper handles. Whether a policy, whether a pod specification misses, does not have a particular label, or if a particular pod has a particular label, it should only be invoked in a particular namespace. Those are the kind of policies that gatekeeper would be able to enforce. KubeArmor, I guess the level of control that KubeArmor does is at a slightly, it is a very different level.
Awesome, thank you.
Thank you. Thank you very much. Yeah.
Oh no, please continue.
Oh no, I was just going to wrap up saying that thank you for the question, and if we would love to see any feedback. It's an open source project. It's an Apache license, so anyone can take it, change it according to their own will. We would love to get the contributions back. It's going to be a long-term project.
Hey, Rahul, where can people get more information? Is there some links that we have that you could post to the channel?
I posted this GitHub page link.
Oh, cool. Gotcha.
Yeah, and it has the Slack information. We are also building up a website specifically for KubeArmor, but again, it is going to just additionally add some blogs and make sure that the demo videos are get shown up.
And we're collecting these links, and we'll be sure to share them out with the group after we're done here tonight for sure.
Thank you very much, Andrew. Yeah, Phil, I think you can continue from here, and Phil will be giving the context of VAE and Provenance engine that Accuknox is building on. Phil,
Okay, yeah. Thank you.
My stop share does.
Yeah, you're gonna stop sharing.
Okay. No, my stop share doesn't work. So can you just override? So for some reason, Zoom's stop share doesn't work in Linux native environment. I know, or maybe it's my machine problem. If you directly go ahead and share your screen, it should take away the control from me.
Go ahead and give it a try, Phil. See if it'll let you.
Can you guys see that?
Yes.
Okay, so that works.
Excellent. Hey, Rahul, totally unrelated. I'm rocking Ubuntu over here. I don't really have that.
Oh.
It's a little bit easy. It's a little bit nicer for me. I couldn't tell just by the window manager you're using. What are you rolling over there?
Yeah, I'm on Genome. So it's the standard Ubuntu 18.04 Genome window manager that I'm using.
Oh, that's interesting. Okay, sorry. Go ahead. Phil.
Okay. Hey, can I do a quick time check just to sort of see where we are in terms of your time and your availability? Just so I'm.
Yeah, totally. We're looking at 35 past the hour. We've got this place until about 8:30 or so. Okay.
I'll go fast and just sort of give you guys an intro into sort of the things that two of the things that we're looking at that is sort of more longer term in terms of trying to solve some challenging problems that have been expressed to us by people we've been talking to, particularly organizations that are dealing with real world problems in large scale container environments. And they have some fundamentally hard challenges. And we're looking at strategies, which is a natural thing that we do, look at strategies to overcome those challenges. I'll talk about two challenges that we have been looking at and trying to develop solutions to overcome, and sort of the progress we're making in that, if that makes sense. As a little bit of background, I'm Phil Porras. I'm in Menlo Park, California, which is in the Bay Area, not too far from Stanford. I'm part of the Stanford Research Institute, but also developing out core technologies for Accuknox and transitioning those over. And so I'm trying to work through, the core algorithms that can be used, and the productization, the deployment, the integration with customers is really the depth of where Asif and Rahul really play a critical role here in trying to do those sorts of transitions. And that's a natural role for SRI and for a person like me to be in. And so I'm going to talk about some of the challenges that that we're taking on, and I'm going to talk about two in particular. And Rahul's already sort of talked about KubeArmor and the issues that it deals with and sort of its novelty and uniqueness. I'm going to talk about one problem in the area of process level monitoring and how to scale that in containerized environments. Generally speaking, we're looking hard at the problem of dynamic runtime security protections in container environments, which go from the networking to the fine-grained application controls that are addressed by things like KubeArmor, as well as from the perspective of data flow and trying to understand where sensitive data flows in complex containerized pipelines that interact with lots of different data brokers inside cloud services. So two topics I'm going to talk about. I'll talk a little bit about the work we're doing where we're applying deep learning to accelerate process monitoring and forensic publication. I'll sort of talk about some of the motivations of that and kind of where we are with that. And then also this problem of the data-centric policy perspective of tracking sensitive data as it's being processed by complex containerized pipelines and interplaying with data services. And how do we track and understand where our data goes, essentially, in containerized environments? That's a second challenge. That's a visibility challenge. And most of the groups that we've seen when it comes to this notion of live data governance, that problem space is really in its nascency, as well as the problem of trying to scale container security monitoring, container monitoring when you're dealing with very large ecosystems. So let me start just by sort of giving you a quick overview of sort of the deep learning strategies, because lots of people apply deep learning to the computer security field, fault analysis field. We're trying to address two core questions, which is, as we deploy out containers and we're operating them, can we detect which of the containers in some massively scaled deployment of containers are not aligned with the expectations of the production runtime? Essentially are behaving outside of some notion of what stable operations for that container should look like. Can we scale up a strategy for doing that? And when you think about fine-grained understanding of how processes are performing, you're usually talking about some dynamic analysis that involves some sort of system call, or process level, I should say, process level analysis. And system calls and eBPF really in DevOps communities pop up as a strategy to do that with some sort of performance concern. And that's something we want to do, but that's something we want to do in a manner that can really scale. So one challenge is, how do we recognize containers when they're operating in a stable, understood manner? And when they're not, how do we provide the fine-grained forensics that you would need to try to understand what might be causing the container to operate out of spec or out of your production runtime expectations? Is it an environmental error? Is it an error occurring with the application? Is it something more benign, something that you just didn't expect, or you hadn't been exposed to that kind of input? Or does it appear to be some sort of security-related issue? We'd like to be able to pivot from being able to recognize when a container is operating in an unstable manner to producing forensics that can be reported to a backend that allow us to do analysis. And that's kind of the heart of what we're talking about here. Can we develop out a smart forensic publishing system or an adaptive forensic publishing system that has the ability to, as forensic data is being extracted from container processes, does some upfront lightweight analysis of that runtime operational behavior pattern, determine whether things are stable, and then from that, produce some sort of decision as to the depth of forensics that you want to publish to the backend repository, with the expectation that if you try to apply this sort of adaptive strategy, what you should be able to do is scale process monitoring to ecosystems where we really can't do scaling at that level. We really can't do process level stability analysis and forensic collection to any significant extent, simply because of the amount of resources that get overwhelmed. Resources aren't just CPU time, although that of course is really important. The local load of doing that sort of analysis on the host that's running the containers, but also if we're going to be reporting those forensics back to a backend server for incident analysis, we're going to have to incur costs for network transport as well as for data storage. And we've been talking to partners. For example, we've been talking to Netflix that runs very, very large container ecosystems. And when you get into the thousands or beyond, the solutions for doing process level monitoring and management of backend repository services becomes quite a challenge. And actually, we've been talking with the forensics team inside of Netflix that really started describing to us this problem, and we started developing out solutions. And the solutions that we began looking at were how do we do efficient, adaptive, robust analysis of processes, which there are good deep learning strategies for doing that can be relatively cost effective. One strategy is using variational autoencoders. Variational autoencoders are very good for this kind of a problem space, and in fact are being used in many different ecosystems for analyzing application or device performance, fault analysis, even for some security purposes. But here we're trying to use it to provide a very quick assessment as to whether a container is stable, and then use it as a mechanism for deciding the depth of forensics. And so in cases where things are unstable, we are going to be delivering the full forensics back to the repository. And you can think of us doing this analysis in terms of intervals. So we'll be analyzing applications for some short intervals, say 30 seconds or a minute, producing an assessment of what we just experienced, and then making forensic reporting decisions based on that. And it turns out that's quite that has quite an impactful reduction in the amount of performance overhead that you end up having to deal with. Deep learning systems take in input. That input for us is derived by a fine-grained analysis of the processes down to the system call level, or using content like eBPF to understand exactly some of the core system calls that are most relevant for diagnosing errors, diagnosing security threats, driving host intrusion detection systems, incident analysis, and isolating out those system calls as things that we want to track within the process, and then developing out a strategy for summarizing those forensics into something consumable by a deep learning engine. What that typically involves is the summarization or the vectorization of the raw forensics into a vector that captures statistics about the forensic data that's being produced by the containers, and then let that drive the creation of a learning model. In the case of VAEs, the production of two CNNs, two neural networks that allow you to do analysis and determine whether this trained model is being experienced by, is consistent with the data that's being produced live when the container runs. So essentially there's a training phase that occurs offline. It occurs with corpuses of eBPF data. It can also occur live, and you can switch into a detection mode. But what a variational autoencoder is very good at doing is taking the raw input, converting it into a lower dimensional space, or into a vector that summarizes various aspects of the statistics that you see from the forensic data, try to decode that further with an encoder that takes the activity vector and produces a very low dimensional latent model of the data, and then a second CNN, a second neural network that takes that very, very low dimensional model and tries to reconstruct the first input, the original activity vector. And in cases where you've trained both the encoder and the decoder and exposed it to data, they're very, very good and very robust and forgiving in terms of being able to look at the activity vector and understand that the new input vector matches that model. And they're also good at recognizing when it doesn't occur. And that is called a reconstruction error. So when the input data comes in describing an activity vector, it goes into the encoder, and the decoder attempts to take the latent model produced by the encoder and tries to reconstruct that data. If we've not been exposed to that data, then we're not very good at doing reconstruction. And we can actually evaluate the extent to which we've been exposed to this particular pattern, this forensic pattern, by doing this analysis. And this is actually, we're capable of doing this on a host with a very, very good computational profile. You can do this with multiplications that really scale well, which I'll talk to in a minute. So here, the comparison of, well, how would you do, how would you compare this kind of analysis of smart forensic, adaptive forensic publishing to standard techniques? So a standard technique would be being able to isolate out a selected group of forensic data coming out of a container ecosystem. So here, for example, we may have anywhere from 10 to 50 containers, extracting out the selected forensic calls, caching them locally, and then at intervals of time, we use bulk write APIs with Elasticsearch to provide that information into Elasticsearch, and then run our forensics. We could, from the back end, in a traditional sense, we could do Elasticsearch analysis and determine what do we see inside of that, the data that we're publishing. That's the standard way you would do it. And then we compared that standard way to the way you would do it with a VAE optimized version of a publishing system, and compared the results, comparing them with different workloads from 10 containers all the way up to 50 containers, where we were pushing containers to produce an average of, for our intervals of time when we did both of these analyses, we were using intervals for flushing at about 30 seconds and generating close to 100,000 system calls per interval. When we do that analysis, we're trying to answer two questions. One is the ability for us to recognize stability, and then the ability for us to push for the forensic data on demand. And the comparison here that I'm showing you is the comparison of what the overhead performance looks like if you're instrumenting 15 containers live on a host. You're running eBPF on a selected set of about 70 security-related system calls, and you're publishing that to the backend, versus you're using a VAE optimized model. And here, both of the containers are operating with sort of a stable execution of the container. So during normal runtime operations, essentially, what would the operating profile look like? And this is sort of giving you a sense of what we're actually seeing when we run standard publishing with bulk API pushes through Elasticsearch. Probably the second table is the simpler one to look at in terms of what does it cost in terms of processing time. These are sort of the delta between what you get from standard publication. And standard publication, there's also this known understanding of saturation, meaning that the volume of, okay, hold on a sec. Yeah, yes. Sorry, I got interrupted. The volume of data and the forensics you produce actually takes longer to deliver to the backend Elasticsearch server than it takes to perform the interval of time. When you get into a situation where it takes you longer to publish the data than it does to create the data, you really have reached saturation. And you start to experience that with standard publication methods. And this is essentially what Netflix was also pointing out. This is what they experience in real life. With a approach of essentially applying a variational autoencoder in front to try to realize whether we've got a stable operating mode or not, and then do selective depth of forensic publishing, you can actually quite effectively optimize the amount of load it takes. So here, for about the same 50 containers, we can do stability analysis and report back our findings and the application modality of what was the application doing in about half a second versus about 28 seconds from the normal method. And then if you were to look at the amount of data that you actually end up having to transport, the network transport as well as the data storage load, these sort of tables give you an understanding of what that looks like. So for processing time, we can cut it down by 2 orders of magnitude. But when you get into network transport costs, which are also significant and costly, particularly in cloud computing environments, you could reduce the amount of overhead by 3 orders of magnitude, and yet still do stability analysis and deliver forensic data to try to understand when the system goes awry. And then the data storage cost inside of Elasticsearch, which can do compression, is about 1/3 of the cost of the network transport. So we're talking about substantial performance gains of 2 orders of magnitude, 3 orders of magnitude for network transport, and then 4 orders of magnitude for data storage. So we could see ourselves developing out these algorithms such that they can be deployed into large container ecosystems and provide that fidelity of telling you which containers are not stable and which ones aren't, and then also providing you the forensic analysis to do fault or security analysis when things become unstable. And in fact, we also do stability analysis using the variational autoencoder technique, where we run through different cycles, for example, running Nginx in a stable mode, and then slowly migrating from Nginx to logging in, performing file downloads, starting to hijack or replace Nginx, and recognizing the extent to which the variational autoencoder can recognize those different patterns occurring within the container and generate meaningful statistical variations that tell us we are no longer operating in that stable expected runtime. And so this can be repeated not just for container hijacking, very blatant events like this, but also when the ecosystem goes down, applications encounter errors, other security-related or network-related security attacks produce these impacts. When they impact the standard operation of the container as we've trained on it, we can recognize those and start to provide forensic reports to the back end. So in a nutshell, that's what we're exploring with respect to how do we make things very stable, be able to recognize things when they're stable in a very efficient manner. And then also, how do we provide the backend forensics to try to do some diagnosis as to why they became unstable? And we think we're developing out, using a deep learning strategy, a method for doing that that's going to allow us to scale, typical fault as well as security analytics to container ecosystems that it's very difficult to do now using something like the variational autoencoder approach. I'm going to pivot now and talk to you about another thing that we're studying, which is the application of an area of research that's been going on in the computer security domain for almost a dozen years. And this has been going on inside of SRI for quite a long time as well. And that's the analysis of something called Provenance Analysis, which is an analysis that's designed to try to understand how applications interact with data, to try to understand the origin, the integrity, the veracity of data in computer environments, and developing on systems that do this in the large. This has been ongoing research that's happened inside of a variety of different places, but SRI has been doing some thought leadership in this for about 12 years or so, and we've developed out a substantial provenance engine called Spade for doing exactly that. And the principles of provenance actually go back further into basic computer science of trying to understand the flow of the sources of where data came from, for the purposes of trying to understand the validity or the veracity of the data that you're doing analysis on. And in the context of the work that we've been doing, it's really trying to translate those underlying provenance primitives to deal with actual applications on host. Trying to, within a wide range of operating systems and audit forensics, build provenance graphs that allow you to understand how data flows between applications, processes, and data stores. What Accuknox is starting to look at is how do we apply provenance to try to do sensitive data flow tracking in really complex environments like containerized ecosystems where processes operate across different hosted hardware. So you're actually doing diverse distributed computation across different processes, and you have to propagate provenance, as well as the fact that in containerized ecosystems, much of the interaction with sensitive data and the storage of data doesn't happen as a container local event, but happens with interplay with lots of data access brokers. So what is a provenance graph? A provenance graph is a way to sort of map out the interactions between data artifacts, which in the parlance of operating systems can be a wide range of data objects that are used to store and convey data. But you can think of them simply as files if that's helpful to think about, as well as agents that interact with that data. So processes as an example. And a provenance graph internally sort of defines a distinction between those processes that interact with data and those resources that store data. And a provenance graph provides you a timeline of interactions that allows you to track how sensitive data propagates through application environments in operating systems or across distributed environments. So here's like a very simple example of a provenance graph that shows the links between processes that read and write data objects, the initial labels that you would assign to data objects. For example, you may be trying to develop a containerized pipeline for, say, a pharmacy front end, where initially you may have to deal with patient private records, where I have to look up whether or not you're allowed to purchase a certain drug. Then I have to move to the PCI realm of dealing with payment information that you might submit to me that is going to allow you to purchase the drugs. And then of course there's a customer database that may be very business private. There's lots of different data that sensitive data containers have to interact with. And what we want to be able to do is answer the question, where did all the patient private data get stored and where did it come from at any moment in time for a given application, as well as be able to do similar auditing for financial data, for anything that you might deem as sensitive, and be able to deal with the fact that you're dealing with data from multiple sensitivities and you're allowing that data to be accessed and written by various processes that can also establish network connections, that can store data inside of data shares, S3 buckets, databases, etc. And we need to be able to track that information and produce an audit that tells us where sensitive data is going, as well as establish policies that can warn us, for example, if sensitive data is being pushed out to a location that you don't want it to be pushed out to. For example, a public S3 bucket. I don't want patient private data to go there. How do I develop a strategy for building such policies, and then in real time, as these containers operate, be able to answer those kinds of questions? And we're using Provenance to do that. And so we're developing out an algorithm for actually, or basically a system for being able to instrument containers, again, using the same sort of instrumentation we're using for variational autoencoders, to understand at the process level, even at the system call level, what is happening inside of the process, as well as its interactions through libraries and through the various different interactions with data access brokers, where they're getting data, where the sensitive data is coming from, and where they place that data, where they send that data. And so we're developing out, based on that spade technology that SRI has been developing, a solution for doing live data governance under that method, for that objective. I'm going to stop there and open it up for questions. But there's an example of two different works that are happening in the computer science laboratory that really help address two critical problems in container ecosystems. One, how do I do scalable monitoring, understand container stability, and then provide the forensics that will allow you to understand not just when things go unstable or no longer follow your expectations and how you want them to operate in production, but further, how do I actually collect the data that will let me try to assess what happened? So that's what we're doing with deep learning strategies. And then in the context of how do I actually implement data-specific policies to understand how data flows in really complicated environments like Kubernetes pipelines that are deployed in public clouds, as well as access backend data services. How do I track that sensitive data? And there, we think Provenance engines provide an already scalable way of moving forward on answering those questions. And we're developing out a Kubernetes deployable version of the system that I'm talking about, of that spade Provenance engine that lets us do that. So I'll stop there and answer any questions you have about it, or if you have any further questions for Rahul.
Yeah, and if you don't feel like unmuting, feel free to drop questions and comments over in the chat, and we'll be sure they get the attention.
Thank you very much. This was a great session. Thank you. Thank you. It was very interesting.
Oh, thank you. Rahul, do you have anything to add, or Asif?
That pretty much, VAE Provenance along with KubeArmor, it provides you kind of controls which can, which will make sure that we can apply least permissive policies based on the output of VAE and Provenance to the data systems out there using KubeArmor. So that's an eventual plan for Accuknox in the long run. But yeah, we have to make sure that we have individual pieces working in an isolated way. They are completely separately, functioning modules. Thank you for the questions, and thank you for the for listening us out. We would be happy to see you on the GitHub and hear out anything specific that you would be looking from such kind of open source.
Yeah, and to add, I think between KubeArmor and VAE and Spade, we sort of provide, and if you add network security to the mix, you get a 360-degree approach to container security at the container level, not at the admission controller, not at the firewall level. This is every single pod, every single container can be controlled, and this is more for lateral attacks that happen once your containers are already infected, once your supply chain is already compromised. This technology can sort of help you with with those kind of scenarios, right? So combining all of this is really useful, and we are actually building an exciting proprietary solution on top of that. Of course, the large part of it is going to be completely free and open source. We'd love for contributions, involvement. Feel free to check out the GitHub page with the name QBarmer. Thank you.
Indeed, yeah. Thank you for your time as well. Really appreciate the opportunity to sort of talk to you about what we're doing. It's always fun to be able to talk about the things we're working on.
Can we get this deck as well? It was really good. It was really nice.
Definitely. We've jotted down the, we've got the link and we'll send it out to the group later tonight.
Thank you. Thank you.
I'm happy to share my slides as well, if that's helpful.